Hey folks, this video is about waves and their interactions. So first off, what is a wave? A wave is a disturbance that is transmitted from one place to the next with no actual transport of matter. All waves are started by some type of vibration, and the waves, the purpose of them are to transmit energy through space and time. They do not transport matter. Energy is transferred through matter by a wave. There are a few different types of waves. We have mechanical waves, and those have to have a medium to transfer through. They have to transport through matter, some type of substance. Mechanical waves cannot be transmitted through a vacuum, such as space. Some examples would be like a jump rope. The medium for the jump rope, if you swing it, would be the rope itself. A slinky, when you move a slinky back and forth, a wave can go through it. And the medium for that is the coils of the slinky. A wave in water, where the medium is the water. An earthquake, where the wave travels through the Earth's crust. Or sound, which is a wave that travels often through the atmosphere. Electromagnetic waves, however, do not need a medium to transfer. These are things like light, radio waves, gamma radiation. A lot of these things travel through our space. They're called electromagnetic waves because there's two components to the wave. There's an electric component and there's a magnetic component. So anytime you have electricity running through a wire, it also puts out a magnetic field, and those are electromagnetic waves. The vibration that causes electromagnetic waves is the vibration of an electric charge. There are two other ways to categorize waves. There's transverse waves, where the source of the wave is moving up and down while the wave itself is moving forward. The source and the direction of the wave are perpendicular to each other. These are most of the waves that we think of right off the bat, like water is a transverse wave. Parts of the earthquake is a transverse wave. If you swing a rope back and forth, that's also a transverse wave. These could include electromagnetic or mechanical waves. They don't necessarily have to have a medium to go through. And to describe them, we use the wave equation, which we'll talk about soon. Longitudinal waves, they're also known as compression waves. They travel in the same direction as the source that's creating them. They can only be mechanical waves because they require a medium to travel through in order to increase and decrease the pressure, which is known as compressions and rarefactions. Sound is an example of a longitudinal wave. That's why sound doesn't travel through space. To describe a wave, there's three different things we could do. We could talk about the speed of the wave, which is measured in meters per second. That's how fast the wave is going. We could talk about the wavelength, which is the distance of one wave, or it's the length of one wave. So if you follow this wave around from one point all the way till it hit the same point on the next one before it starts to start over. We usually just talk about from crest to crest, or the peak of each wave to the next one. And we measure that in meters because it's a length. And then lastly, you could talk about the frequency of the wave. The frequency is if you put a gate right here and you measured how many waves go past that as it's traveling this way, how many waves go past that in each second, then that frequency is measured in waves per second. But waves isn't really a unit that we use, so we call it per seconds, which also could be written as s to the negative 1, or we say hertz, which is also abbreviated Hz. So as we were talking about the three different ways to describe waves, you may have noticed that each of those ways had a unit attached to it, which may have got you thinking, oh no, there's another equation. And if that's the case, you would be correct. So we have the speed, which again is measured in meters per second. That speed is equal to the wavelength, which the variable we use is the Greek letter lambda, times the frequency. So as you're thinking about that, that should make sense because you have meters per second is equal to meters times per second. And when you do meters times per second, you get meters per second, so everything works out. So there's three different ways you would use this equation. If you're looking for speed, you'll use the v equals lambda times f. If you're looking for the wavelength, you'll take the velocity and divide it by the frequency. And if you're looking for the frequency, you'll take the speed and divide it by the wavelength. If we think about how mechanical waves travel through different types of matter, the key idea is that the closer the particles are together, the easier it is for a wave to travel through. And of course, the longer a wave has to travel, the more energy it loses, so it tends to slow down over time. But if you're just thinking about how fast a wave is going to travel through a particular medium, you could compare different mediums together. So maybe dry air versus wet air. Wet air has a lot more particles in it, a lot of water particles in it. So since there's more particles, they're going to be closer together, and that makes the wave easier to travel through wet air. A solid versus a liquid, a solid's particles are much more closer, where a liquid has a lot of room between the particles. So a wave will travel much faster through a solid than it will a liquid. Same for a gas versus a solid. It's going to travel much faster through a solid than the gas because gas particles are way far apart from each other. And if you think about a metal versus wood, a metal's particles are much closer together than a piece of wood. It's much more dense. And that's why a wave is able to travel faster through a piece of metal. So if you think about if you tap a hammer on a piece of metal, you usually hear a really high-pitched ringing sound. That's a higher frequency, which means that it's got a faster speed. If you tap a hammer on a piece of wood, it's usually a much lower sounding pitch. It's not quite as high-pitched, which means the wave is traveling much slower, has a lower frequency. There are three basic ways that two waves can interact with each other. And to help us picture this, we're going to think about transverse waves, more likely specifically mechanical waves, because they're a lot easier to see and think about. So we call it interference when two waves run into each other, and there's three types of interference. There's constructive, which is where the peaks of the waves line up and the height of the wave gets much bigger. Partial destructive, where they're not perfectly out of line with each other, they're just kind of part way out of line. The crests aren't lined up, and the waves aren't completely unaligned. So the amplitude or the height of the waves tend to decrease, but they don't go exactly to zero. And then there's complete destructive, where the crest of one wave lines up perfectly with the trough, or the bottom part, maybe a valley if you think of it that way, of another wave, and they cancel each other out, and it takes the whole wave to zero when they run into each other. Sometimes it's easier to look at wave interactions if we think of real-life examples. So let's go through a couple examples. If you think of music, sound usually travels as a longitudinal wave, especially when it goes through the atmosphere. So when you have compressions that line up with each other and they add together to the volume of that sound, this happens really well when you're trying to tune two instruments, or maybe you have two people singing that are just slightly off pitch from each other. They don't have quite the same frequency, so the waves are different distances apart. And at different moments, the heights of those waves, or the compressions, in the example of sound, can add up to each other and increase the volume. And when we hear that, it's a really weird sound. It's not just the one note that we're used to listening to. There's what we call beats or pulses, where there's points where it's really loud and there's other points where it's really soft. You can also think of water, which would be an example of a transverse wave. If you're sitting in a swimming pool and you take with your left hand, you slap the surface of the water at a certain speed, or frequency rather, and your right hand, you go maybe with a higher frequency, you're slapping the top of that water faster, those waves will eventually crash into each other, and where the crests of those waves run into each other, that's going to be a much higher wave than it was before. Or vice versa, if maybe a crest and a trough, or the top and the bottom of a wave run into each other, they might cancel each other out. So instead of just talking about when two waves interact with each other, we could talk about how a single wave interacts with a wall or some type of boundary. So say you have a wave here, you have a string that's tied to a pole. And you take that string and you move the end up You're sending a wave that looks like that all the way down the pole. You've probably done this before with a friend in a jump rope where you kind of whip the rope and you see that wave travel. And it looks the same as it just travels down the rope. Well, if the rope is tied to the end there, then it doesn't have a place to move. And what happens is the reflection of that wave comes back looking the opposite as it did up there, I guess. More accurately, would look like that. So the wave that you're sending forward, we call that the incident wave. And the wave that's coming backwards, that's the reflection. It reflects off of the wall. If the wave happened to be attached to, or if the string happened to be attached to a pole, but maybe it was tied to a washer and that washer was just sitting on the pole, we call that a free boundary. The one over here would be called fixed. What if you took that rope and you sent the same exact wave in, the same incident wave, the reflection, since it has the ability to move, when that wave gets down to here, it's going to come back up, and it's going to be sent back the same way that it came. So those are the differences between a fixed and a free boundary wave, what happens when they hit those types of boundaries. When a transverse wave changes through a different medium, in other words, it changes from one medium to another, there's usually some type of change there also. If the original medium is less dense than the new one, so maybe it's like a thin rope to a much thicker rope, the wave, once it hits that point, will continue on, but it'll be much shorter, and it'll also reflect backwards and upside down, much like it would in a fixed boundary. It's going from a more dense to a less dense medium. It's going to act more like a free boundary in that the wave doesn't invert itself. It does reflect back, but at a much smaller amplitude than it started with, but then it continues on with a higher amplitude through the less dense material. Electromagnetic waves have a constant speed that we refer to as light traveling through a vacuum, and it's 3 times 10 to the 8th meters per second, or about 300 million meters per second, and we commonly refer to that as c. However, when electromagnetic waves have to go through a medium, they tend to slow down because they have to go through the particles. So in a vacuum, light just travels straight through, but when it runs into a medium, it's got to hit an atom or a particle, and it goes through the particle, and it's got to be re-emitted by the particle, and that slows down the process because it has to go through each of those particles to get through the medium. When we think about the electromagnetic spectrum, it helps to think about the wave equation. So the speed is equal to the wavelength times the frequency in a vacuum. But we could also think of the speed of light as being constant in any type of single medium. So as it's traveling through the atmosphere, it doesn't really change speeds. If it's traveling through water, it doesn't really change speeds. So if we just think about the electromagnetic waves that we deal with on a normal basis, the whole electromagnetic spectrum deals with the longest types of wavelengths all the way down to the very shortest types of wavelengths. The longer wavelengths, or lower frequencies, include things like radio waves, which have to travel long distances, microwaves, infrared, which is what's used in your remote to change the channel on your TV. And then as we get up to a higher frequency, we start to get to a point where we run into visible light. And that is all of the colors of the rainbow, Roy G. Biv. Starting with red, which has a longer wavelength, and then we end up all the way up to violet, which has a much shorter wavelength. And then as we increase our frequency or shorten our wavelength, we run into things like ultraviolet rays, like rays from the sun, X-rays, and gamma rays. It's important to note that as you look at that whole electromagnetic spectrum, the visible light is only a very small portion of that. We use electromagnetic waves in a lot of ways in our life. Our cell phones run off of types of radio waves. The internet that we use sends out Wi-Fi signals as a type of wave. The X-rays when we go to the doctor, and things like that. But only a small portion of that is stuff that we can actually see.